It's my pleasure to introduce Matt Kerr from Washington University in St. Louis, and he's going to speak about differential equations and mixed Hodge structures.
Thanks, Paimon. Right, so the subtitle of this talk is sort of how differential equations know the asymptotics of the variations of Hodge structure they underlie. The basic idea being that through some sort of interesting and slightly devilish complex analysis, you could tease out information which is either extremely painful to extract on a case-by-case basis about asymptotic Hodge theory, or uses deep work in mirror symmetry. So, you know, you can, there were ways of computing limit mixed Hodge structures at maximal unipotent monodromy points before this method, certainly. I mean, the computations in the original mirror symmetry paper by Candelas, De La Osa, Green, and Parks amount to, in part, a limit mixed Hodge structure computation. But that computation is somewhat painful the way they do it. And there's also work on integral mirror symmetry by Hiroshi Iritani and others that can give you the same results in a more general way, but these methods are more general still, and they're less mysterious because the whole content is just in the method, and it's short, a little bit mysterious, but it's short and in closed form, and everything is done in terms of gamma functions. So let's start by talking about a few examples, or the types of examples that I have in mind. And by the end of the talk, I will at least be able to define what is a motivic gamma function, which is this object introduced by Bloch and Vlasenko a few years ago that had been conjectured by Vasily Golishev and others. So here's two examples, basically. So all of the variations that I'm going to deal with will come from families of Calabi-Yaos over P1 with finitely many singular fibers. Let's start with the Legendre elliptic curve family pulled back by t goes to t squared, essentially. So we have a family of elliptic curves, we have two homology cycles, and a family of holomorphic forms, dx over y, and I can consider the periods of dx over y over alpha and beta. And the alpha period is straightforward. We have just these coefficients here, nothing outlandish. But then when you come to the beta periods, you have a log times the alpha period to denote that, in fact, as you go once around the origin, beta changes by going to beta plus 4 alpha. And then you have this annoying analytic part, which is a little bit uglier. You have this multiplied by an times t to the 2n. So this is the kind of thing that comes up when you have periods. You have a holomorphic period, perhaps at the origin, and then you have a period with logarithmic singularities and some interesting analytic part. Both of those periods are killed by the Picard-Fuchs operator L, shown here. And throughout this talk, D is going to mean logarithmic derivative. The Hodge decomposition on cohomology then varies in T. So H10 is spanned by mu T, H01 by its conjugate. Mu T is just this form here. And it's measured against the Betti cohomology by the periods. So you have sort of two bases of cohomology, a Betti basis and a Hodge basis, and the change of basis matrix is what the periods tell us about. And then writing F1, H1 for H10, the H1 of ETs and F1 of H1 of ETs glue together to yield bundles. This is the cohomology bundle, this is the Hodge line bundle over P1 minus 4 points, where this elliptic curve degenerates. And then finally, you have that the Gauss-Manin connection differentiates periods in the sense that nabla D applied to mu, and then you take the period of that is the same as applying D to this period and so forth. And so by abusive notation, I can say that nabla L, where I simply substitute in the Picard-Fuchs operator, kills the cohomology class mu. And henceforth, I will just write that as, L mu equals 0 for short. Okay, so here's a much more general example that goes to higher dimension. I take a Laurent polynomial in n+1 variables, phi, and I assume that its Newton polytope delta is reflexive. So that means it has integral polar polytope. So here's an example of a reflexive Newton polytope for this Laurent polynomial. And in this case, the origin is the unique interior integer point of delta, and we can consider the level sets of the Laurent polynomial in GM to the n+1. And those level sets have smooth Calabi-Yau compactifications, at least if the Laurent polynomial is what we call delta regular, with Hn0 equals 1. So this is a Calabi-Yau condition that's inherited from the fact that the origin is the unique interior integer point of a reflexive polytope. In fact, we can write down a holomorphic n form as follows. You take the wedge of the d logs of the coordinates together, divide by 1 minus t phi, the equation of xt, and then take Poincaré residue. And that gives me a holomorphic n form on xt. That spans Hn0 of xt. And more generally, we can consider the Hodge flag fkhn. And as t varies, the Hodge flag yields a flag of holomorphic subbundles of M, with the last one being the Hodge line bundle. One has canonical extensions due to Deligne of these holomorphic subbundles and the cohomology bundle itself. And these give vector bundles over P1. And the main thing to know here is that Fne is actually generated by this mu, except at t equals infinity, where you have to multiply by t. So in this particular family of examples, the Hodge line bundle always has degree 1, and mu is a section with a simple 0 at infinity. And the rest of the lecture, I'm interested only in the case where all the Hodge numbers are 1, for simplicity. Now, since this Gauss-Manin connection, nabla D, which I'm going to write just as D, sends Fk to Fk minus 1 by Griffith's transversality, we will generically have that mu and its nabla Ds are enough to span M under this assumption again. So we have a rank n+1 cohomology bundle, and these give sections that span it and all of the Hodge flags if you take the right subsets. And we can arrange this when n equals 3 as follows. By work, this being this case, by work of Batyev, H21 can be given by the number of integer points in delta minus the number of integer points on the interior of facets, minus 5. So for the smallest deltas, in fact, these are just 0. These contributions are 0, and this will be 6. So there are a bunch of pentahedra that are reflexive that give you exactly 1 for H21 of xt. So for example, the most famous of these is to take phi to be the sum of the coordinates, the toric coordinates, plus 1 over their product, and that gives you the Miraquinic family. We can compute a period in a neighborhood of t equals 0 by taking epsilon naught to be the cycle invariant about 0 and writing for its period this. Okay, so because mu t is the residue, the Poincare residue of this thing, and this is the so-called tube on this cycle. Tube and res are adjoint. So you get this calculation. And now we can expand 1 over 1 minus t phi in power series like that. And then you see by the Cauchy integral formula that just the constants in these terms here appear as the solution of this integral. So these are the constants, the constant terms in powers of this Laurent polynomial phi. And in this particular case, for this particular phi, they are just 5L factorial over L factorial to the 5th. So that's the Marquinic period. And that's killed by the hypergeometric Picard-Fuchs operator, where I'm just rescaling t to t tilde, and noticing that this is a 4f3 with these coefficients. And so you put those coefficients in here and write down the standard hypergeometric fourth order operator of degree 1, hypergeometric. Okay, any questions so far? So those are just some examples so that you know what I have in mind when I go to the more general formalism.
Matt, could I just ask?
Sure.
For all the Hodge pieces of the XT, is there a combinatorial interpretation?
For n equals 3, this is in Batuev's paper. I think when n is bigger than 3, you run into, maybe when n equals 4, it's not too hard. When n gets very large, you run into problems with singularities and the toric variety and the fact that there doesn't exist a maximal Crepin partial desingularization in his language. But I guess for nice enough polytopes, for nice enough reflexive polytopes, you could probably find a formula in his Duke paper from 1993.
Thank you.
It's just higher dimension is always worse. Higher dimension, you want to work with differential equations instead of varieties. Any other questions? All right. So here is the general setup. I want to assume that I have a smooth projective n+1 fold with a projective morphism to P1. Then I take the complement of the discriminant locus sigma, call it U, over which the restriction of F is smooth. And I take a point in U near 0. 0 is going to be a point in the discriminant locus. So here is a picture of the discriminant locus. The black points are the points in the discriminant locus, and P is a point not in the discriminant locus that's close to 0. And I will call sigma cross the points of the discriminant locus different from 0 and infinity. Okay, so the point closest to 0, so I'm assuming that there is a single point closest to 0. That will be called the conifold point and labeled C. And now I just assume that I have a motivic variation of Hodge structure arising from this kind of situation. So I have a variation M with connection nabla arising in the nth cohomology bundle of XU over U. I can also write this as a D module. So the differential operator is L. And then I assume I write FK for the Hodge flags inside of M. I mean, all of this is written as an inclusion here because I'm not assuming necessarily that M is the full cohomology. I'm assuming that it's a subvariation of the nth cohomology of the fibers. This is particularly important if I want a 1-1-1 Hodge structure in dimension 2. of fibers, since the fibers are going to be K3 surfaces. So those will be Picard rank 19 K3s, and this will be an actual sub. The notation blackboard M is going to denote the Q local system inside M. And then I assume that I have a polarization that comes from fiber-wise integration of forms and intersection of cycles from M cross M to Q. Then the assumption from before that the Hodge numbers are all 1. So Calabi-Yau type with Hodge numbers 1, 1, 1, 1, 1. I assume that the monodromy about the origin is maximally unipotent. So the mixed Hodge diagram looks like this. All of the classes in the limit are of type PP, and the monodromy logarithm N naught, this log of T naught, is mapping classes from PP to P minus 1, P minus 1. And at the bottom here, we have a class epsilon naught. This is really at the bottom of the dual local system, which is homology. This is our invariant topological cycle about the origin. So I'm assuming that the rank of the invariants under T naught are 1, and that epsilon generates those invariants in homology. All right, on the other hand, I assume that the X's are places where you have conifold monodromy. In other words, the fibers have only ordinary double point singularities and only 1 each. So that the rank of TCI minus the identity, the monodromy about each of these points, is exactly 1. Okay. So this TC minus I, the image of TC minus I, will be generated by a conifold vanishing sphere. The rank of the combined invariants of both monodromy about 0 and monodromy about C is assumed to be 0, which is equivalent to saying that if I take TC minus the identity and apply it to the invariant cycle about 0, then I get something non-zero, this delta. Okay. And so that delta is considered to be a homology class in the fiber at P. Okay, P is our base point, so everything is sort of considered at P. So now I take a section that's nowhere vanishing away from infinity of the canonically extended Hodge line bundle over P1. And then I can assume that mu is normalized. I mean, we think of mu as a family of holomorphic n-forms. I assume it's normalized so that its period against epsilon naught, the invariant cycle, which has to be holomorphic at the origin, has constant term 1. Okay, so everything is set up as in the examples in section 0. Now I can also canonically normalize my Picard-Fuchs operator as follows. First of all, I'm going to write it in the following way in terms of powers of the logarithmic derivative t dt. It has order n+1 because that's the rank of the connection, the rank of the cohomology bundle. I assume that things are normalized so that these are polynomials in T. And of course, L has to kill mu. I assume that these are taken to be relatively prime polynomials and that Q naught of 0 is equal to 1. Okay. The fact that this should have a non-zero constant term is it corresponds to the fact also that if I write the Picard-Fuchs operator in this way, then P naught of D, the coefficient of the 0th power of T, is D to the n+1. And that follows from the fact that I have maximal unipotent monodromy at the origin. So in any case, I have uniquely normalized my Picard-Fuchs operator And I also make the assumption that the degree of the Picard-Fuchs operator is exactly equal to the number of conifold points. A priori, it could be greater than or equal to the number of conifold points, but I'm assuming that they're equal. And that's a pretty standard situation. Like if you start with any Minkowski polynomial, like in the classification of Fano varieties done by Cordy and Coates and company, then this will always be true. Okay, so we have order n+1, Picard-Fuchs operator, degree d, which is the number of these points. Okay, the hypergeometric case is degree 1, where there's a single conifold point. Somewhat more interesting are the cases where you have 2 conifold points. Many examples of that type arise in the Fano search program, and also are they also underlie the irrationality proofs of a priori, among other things. Okay, any questions on the setup? So it's you know, very constrained, but it's also the constraints are fairly standard in the setting of Landau-Ginzburg models of Fano varieties, for example. Okay, so I'll go on to periods. Start with Betty periods. A lot of what I do will be now restricted to this common neighborhood of 0 and the first conifold point. So just this small neighborhood here. So it turns out that it's easy to show that there exists a unique extension of this invariant homology basis element to a basis of homology at P such that the monodromy logarithm at 0 sends epsilon j to epsilon j minus 1, and TC minus the identity sends epsilon j to 0. So epsilon j is invariant about this point for every j bigger than 0. So only epsilon naught is not invariant under this. And TC minus I applied to epsilon naught, let's see, where was it? TC minus I applied to epsilon naught was here, and it was defined to be delta, which is our conifold vanishing sphere. Okay, so for periods, I put epsilon j of t with this font of epsilon equal to the pairing of mu against epsilon j. So asymptotically, as t goes to 0, these periods look like log to the j of t over a constant. On the other hand, we have the conifold period, the period of mu over the conifold vanishing sphere. And as t goes to c, that period is asymptotic to t minus c to the n minus 1 over 2. Okay. After all, it is a vanishing sphere. So at least for n bigger than 1, you have vanishing of that period. Okay, so a different basis of periods is given by Frobenius periods. These are not Betty periods. They're not Q-Betty periods. And they're constructed as follows. You write down a formal generating series like so. And here m goes all the way to infinity. And S is just some new complex analytic variable that I'm taking the generating series n. Okay, and we assume the following two properties. That the Picard-Fuchs operator applied to this phi, Picard-Fuchs operator is in T, remember. The Picard-Fuchs operator applied to phi gives this inhomogeneous term S to the n plus 1 T to the S. And the action of monodromy about the origin applied to phi gives e to the 2 pi I S phi. Okay, so what does this amount to, say, in the case n equals 3? Well, it tells you that you have, because you're going to have an s to the 4 here. If I take coefficients of s, s squared, s cubed, and so forth, the coefficient of s to the 0 gives me L phi naught equals 0. The coefficient of s to the 1 gives me L phi 1 equals 0, and so forth until I get L phi 3 equals 0. So I have 4 bona fide periods here. Then when I get to n equals 3, I have s to the 4th. And applying L to phi to the 4th, that tells me I need to get, let's see. So I have to expand this thing as a power series in S as well, with coefficients in T given by things like 1 log T, log squared T over 2 factorial, and so forth. But the upshot is that you're going to get L phi 4 is 1, L phi 5 is log of T, L phi 6 is log squared of T over 2 factorial, and so forth. So we have this giant generating series of quote unquote periods. Only the first 4, when n equals 3, fibers are Calabi-Yau threefolds. Only the first 4 are actual bona fide periods in the sense of being solutions of the Picard-Fuchs equation. The remaining ones are going to be solutions to inhomogeneous equations of some kind. And these are related to what are called in my paper and Block and Blasenko's paper unipotent extensions of the original D module. I'm not going to go into that very much in this talk, but my main point here is that in order to understand something about the 4 actual periods and their asymptotics as you go to 0, you need to face this entire generating series. Because it's this entire generating series which, rewritten in powers of T, is going to have coefficients that obey a recurrence relation that allows you to compute. So we really do need the entire infinite generating series. Okay, so let's see how we can manipulate this thing. First of all, from the fact that T naught applied to phi gives me e to the 2 pi is phi, well, if I multiply by t to the minus s, and t goes once around the origin, then that will also change by e to the 2 pi is, but e to the minus 2 pi is, and will completely counteract the monodromy of this. So the point is that this thing is T naught invariant. And so that's why I've labeled it phi analytic. So if I expand this now in powers of s formally, the coefficients of powers of s will be analytic functions at the origin. And so I can write them in power series and define AKM in this way. Okay. So now if I multiply again by t to the s and arrive back at phi, there I'm multiplying by t to the s, and sort of reorganize the series, then I find that the phi m's that I started with can be rewritten as combinations of these phi analytics times powers of log. Okay. I can reorganize them in a different way in terms of powers of t with coefficients that I'll call AK of s. And it comes right out of this definition here, that the AK of s's have power series coefficients AJK, where instead of k running, like here, the coefficient, we're looking at coefficients of s to the j with j running. Okay, so I've just rewritten it as a generating series in a different way, in powers of t instead of powers of s. Well, what is this good for? Now I'm going to use the second assumption here. L phi equals s to the n plus 1 t to the s. Okay, so L phi equals t to the s, which I brought over here, s to the n plus 1. Now, here I have t to the s, L phi, And what I want to do is let this d to the n plus 1 chew on this t to the s. That's going to bring down s to the, let's see, n plus 1. Okay, so I have an s to the j coming from here. And I'm going to ignore anything that has positive powers of t in it. So all that I'm just going to ignore. So this is what I have when I've done this computation. S to the n plus 1 equals this sum plus O of t. And then setting t equals to 0 and dividing through by s to the n plus 1 gives me 1 equals this sum in s, in powers of s. And so you can see that all of these have to be 0 except for a0, 0. So that tells you, since the aj zeros, by definition, are the constant coefficients of phi j analytic, you see that the phi j analytics have 0 constant term. That is to say that the analytic part of the Frobenius periods all have vanishing constant term. That's in distinction to the behavior of the Betty periods, which typically will have non-vanishing constant term in their analytic parts. So the upshot here is not only do we have this, but if you can read off from a0 of s equaling a0j s to the j, that a0 of s is identically 1. And finally, we have for the 0th Frobenius period, that's phi of 0 comma t. That's the same as phi 0 analytic and is this sum, which is really just the same as our original 0th Betty period. So overall, the picture here is that we have 0th Betty and Frobenius periods are the same. That's something analytic at the origin. And then when we go to the higher solutions, the Descartes-Fuchs equation, both sets of solutions are going to have log squared, log cubed type behavior at the origin. But the difference is in what the constant terms of the analytic parts look like at the origin. And that's going to be the key to relating the Betty periods to the Frobenius periods in terms of a change of basis for periods. And that is going to be responsible for telling us the limit mixed Hodge structure. I just note here that a priori, this magical generating series phi and the AKs defined here are formal in S. But in fact, because applying L to phi and getting this s to the n plus 1 t to the s inhomogeneous term implies a recurrence on the AMs, you find that since A naught is identically 1 as well, you get formulas for the AMs as rational functions with poles in the negative integers. And so you find in this way that this formal thing phi is really a bona fide analytic function on C minus the negative integers in S and the universal cover of U in T. Okay. Any questions on this? So I've collected sort of the stuff that we need to remember over here. The data about the different homology Betty cycles under n naught, epsilon n goes to epsilon n minus 1, goes to epsilon 0, and under Tc minus I goes to psi. These are the corresponding, these are the cycles, these are their periods, and these are the Frobenius periods. Okay, so let's talk about limit mixed Hodge structure at the origin. The limit mixed Hodge structure, on the one hand, can be thought of as being given by untwisting the Hodge flag and writing with respect to the basis of homology as t goes to 0. Okay, and there's a weight filtration coming from the monodromy logarithm as well. But that's not the version that I want to use that's going to be as useful here. Instead, what I want to do is untwist the local system and compare that with just the limit of the Hodge flag. Okay, so I mean, the two perspectives are completely dual. They're the same. It's whether I apply e to the plus log t and not to the Hodge flag, or e to the minus log t n naught to the homology basis. That will be called the tilde homology basis. And that's what I'm going to use. And then I set omega lim to be the change of basis matrix from mu and its derivatives, Gauss-Montian derivatives, to this untwisted rational basis. And you can compute the first column of this matrix as follows. I just take mu and epsilon j tilde and evaluate at 0 their pairing. The idea of the tilde is that it gets rid of all the log stuff that's impeding, that would make periods blow up at the origin. So expanding this a little bit, it looks like the following. I've applied e to the minus log t n naught to epsilon j mu. And what this does is it simply formally sets log of t to 0 in epsilon j of t, and so it gives me epsilon j analytic at 0. So the constant term of the analytic part of the jth Betty period. So that's what the first column of the limiting period matrix is giving. And by a short calculation, which I won't go through in detail, I mean, it's just saying that the residue of nabla d at the origin is n naught over 2 pi I, and then you can move that over to here. The upshot is that this column gets shifted down with a 0 being put above each new 1 that comes down. So this entire matrix can be read off from the first column. This entire matrix can be read off from the first column because the successive columns are just downshifts of that first column, with the bottom entry being swallowed at the bottom of the matrix. Okay, on the other hand, the phi j analytics have 0 constant term, except for the 0th phi j. So in essence, omega lim is a change of basis matrix between Betty and Frobenius solutions of the original Picard-Fuchs equation. And that's how we're going to compute the limit mixed Hodge structure. Any questions?
Is this the motivation for defining that Frobenius basis in the first place?
Yeah, yeah, it is. Yeah. Okay, so now I'm going to, the first really new thing here is this kappa series. So start with a general calculation about solutions to D modules. So I have my solutions to this Picard-Fuchs operator, and I can apply the conifold monodromy minus the identity to that. And that's going to be, of course, the period of the conifold vanishing sphere. That's all that's there. This is just rank 1. So if I integrate to get solutions to LD, so this would be integration against dt over t indefinitely, then you can write Tc minus I applied to solutions of LD as sort of an indefinite loop integral about C of sol P of L. This also has rank 1 because there's only one basis element of this that's not analytic at C. So now I can dualize. I can take Frobenius dual, and that swaps the D and the L and gives me that this thing still has rank 1. And since psi is a solution to L, hence to DL, psi has to span the solutions here, the image of the solutions under Tc minus I. And now I can just iterate this whole argument. I started with this, I got to this also being spanned by C psi, and I can just keep iterating by applying powers of D. So that means that if I apply Tc minus I to any of these Frobenius periods, even the ones that aren't really solutions to L, but which are solutions to this, by virtue of solving those inhomogeneous equations, I get some multiple of psi of t. And so I can now assemble these into their generating series and say that Tc minus I applied to phi is some multiple by some kappa of S by psi of t, where kappa of S is given by a power series. Once again, this is completely formal, but turns out to be an interesting analytic function. And the behavior of kappa of S at negative integers and at positive integers and at the origin all have different meanings. Roughly speaking, the behavior at negative integers has to do with the original power series coefficients of the holomorphic period. It serves as an interpolation function. The behavior of kappa, when you evaluate it at positive integers, will have to do with algebraic cycles. So it's a very interesting beast. But what we're interested in right now is its derivatives at 0. So if first what I want to do is invert it. And I mean, one thing that's implied by the formalism we already have is that kappa 0 is 1. So it makes sense to invert this as a power series and get alpha mt to the m so that I have this identity. And I claim that the first column of the limiting period matrix is in fact given by these alpha j's. Okay. So I'm going to sort of flash the proof up just so you see that it's elementary, but again, it will go by pretty quickly. The first idea is simply that you want to show that n naught sends phi j to phi j minus 1. This is sort of obvious from the way I've set things up, because that's true of the Betty period, of the corresponding Betty periods. To check that n naught sends phi j to phi j minus 1, you just use this property of capital phi, and then take sort of, use the fact that taking log of t naught, if you will, and taking log of e to the 2 pi is changes it to this. And so then you have n naught phi j Sj is equal to this generating series. And so that immediately implies that. Then the next step is that, you need to show that the change of basis matrix from the Betty periods to the Frobenius periods is just given by the constant terms of the analytic parts of the Betty periods. So that's here. And that's just, again, you write epsilon n in terms of the Frobenius basis and repeatedly apply n naught, and it pops out. And then finally, you want to show that Cj, the Cj's defined here, actually equal the alpha j's. So that, so what you have to do is show that the Cj's have this property, right? Because the Cj's are the constant terms of the Betty analytic parts, and so belong here. These are just that. But we need to show that the Cj's also satisfy this. And so you write this times psi equals, well, kappa j psi is Tc minus I phi j. And now I can bring the Tc minus I out and observe that this is just epsilon L by definition. And then replace the periods by the things they are periods of. Psi is the period of delta. Epsilon is the period of this epsilon. And we know that Tc minus I applied to epsilon L is almost always 0, unless this is 0. And so at the end of the day, you get that this is equal to the Kronecker delta. So it's pretty straightforward. It's a little convoluted, but you end up with this. Okay, so that means we can compute the limiting period matrix if we can compute this kappa. So how do we compute kappa? Well, here's a formula for kappa. Remember that if I wrote phi as a generating series in T, then the coefficients were these capital AKs, and they satisfied a recurrence. So I claim that kappa is given by this formula. This is the conifold point to the S power, and then I just take the limit of AK of S over AK. And that gives a formula also for the individual kappa m's, but this one is more important. So this is an interesting proof. I mean, you have to know something about asymptotics of coefficients of power series based on the behavior of the functions given by the power series at the conifold point, and we can do that. So let's start by defining some weird function b of t to the minus s naught times this big generating series. I'm fixing s equals s naught minus c to the minus s naught kappa of s naught times the 0th Betty or Frobenius period. And now observe that this is invariant about the origin because, first of all, that's that phi analytic that I defined that was invariant by design, and phi naught is invariant about the origin. So we can write the power series expansion of this about the origin and the power series expansion of this about the origin. But what does it behave like about the conifold point? Well, we apply Tc minus I to B to find out. We know that phi becomes kappa psi when we apply Tc minus I. And we know that phi naught becomes psi when we apply Tc minus I. So at the end of the day, I just have T to the minus S naught minus C to the minus S naught. So that gives me T minus C times the derivative of T to the minus S naught minus C to the minus S naught at C. And so at the end of the day, since psi looks like T minus C to the n minus 1 over 2 here, this quantity looks like T minus C to the n plus 1 over 2. Now we need a lemma. And this lemma is really useful. I've used it in other papers since this stuff. And it seems that whenever you're interested in periods of families where you know something about the behavior at a conifold point, this will yield useful information. So if I have a power series, and I know that while it only has a radius of convergence C, it does extend to the universal cover of, P1 minus some points. And moreover, you need to assume it or an integral or an iterated integral of some kind is bounded on this larger cut disk. And now assume that it satisfies Tc minus I applied to B equals some constant times T minus C to the W minus 1. I've taken W here to be a half integer. Then it follows that Bm, the coefficients of the power series, is actually asymptotic to this constant times C to the W minus 1 times gamma of W, that's the usual gamma function, over 2 pi I, and then the interesting part is this. And if I now plug this in to my knowledge of these asymptotics here, I get that the AMs have this asymptotic, the BMs have this asymptotic, what we note as W plus 1 over 2, W plus 3 over 2. And so at the end of the day, that confirms that the limit of BM over AM is 0. And writing out BM, we have this. And so we conclude that this limit is 0, which is exactly the statement multiplying through by C to the S naught, that kappa of S is equal to this. Okay. So this is not unrelated to a priori rationality proof for zeta of 3, by the way, because you have two things that go off to infinity, and then when I combine them in the right way, I take the right real linear combination, it goes to 0. Okay, corollary is that this generating series, which was the inverse of kappa of S, is equal to C to the minus S, AM over AM of S, where A naught of S is 1, identically, and AM is given by this recursion. And so now we have an application to the hypergeometric case that allows us to compute all limit mixed Hodge structures in one blow. So we start off with an operator of this form, standard hypergeometric form. Then phi naught, the 0th Betty or Frobenius period, same thing, will be this hypergeometric function. I am assuming that the conifold point is at 1 for simplicity. And then our recursion tells us that AM of S is AM minus 1 times this product. And sort of completing the recursion, like assembling the whole thing, we get that you get this product of quotients of gamma factors. So now I apply Stirling's formula to compute the limit of AM over AM of S. And that turns out to be just this simplified product of gamma factors. So I can figure out what the alpha J's are if I can do power series expansions of those gammas. So let me do one example. So lambda is 1/5, 2/5, 3/5, 4/5, the Miraquinic family. I use this formula for gamma of 1 plus x to get my power series expansion. And notice here, you have the Riemann zeta values appearing. So then alpha j s to the j, I only need to do the first 4 terms of it to get the 0th column of my 4x4 matrix. And this is what it works out to be. And notice in particular the zeta of 3 here, coming from the k equals 3 term of this. If I rescale t by t goes to t over 5 to the 5th, then that has the effect of multiplying alpha by e to the 5 log 5s. And then that will get rid of all these annoying log 5s here. So remember, rescaling at the origin, changing your tangent vector at the origin affects the mixed Hodge structure. I still have my zeta of 3. And then if I correct the integral basis, this was just for a rational basis. If I use the correct integral basis for the Miraquinic family of homology, then I actually get this, which recovers the limit mixed Hodge structure of the Miraquinic without using either tricks, ad hoc tricks of, as in Candelas de la Osa Green and Parks, or deep mirror symmetry yoga by Iritani. Everything that I use to do this calculation is on these slides, essentially. I mean, even though probably the proofs, or what I gave of the proofs, went by a bit quickly. Now, if I could, maybe I am going to go to a full hour. I'm going to do 5 more minutes of slides just to tell you what a motivic gamma is. Motivic gamma is basically what you get. I mean, when you have a connection, you can take periods of the connection, right? You think of that as a period of the total space. Except I'm not going to take the regular connection that I start with. I start with a connection M, my variation of Hodge structure, and I take its Mellin transform, which is to say I simply tensor it with the rank 1 connection with differential equation d minus s, which is called informally t to the s. And then I take a class, which is a section of M, and I form an H1 de Rham class with coefficients in this Mellin transform by taking M tensor t to the s tensor dt over t. So this is the horizontal, this is the vertical direction, this is the horizontal direction. The horizontal direction gives me this one. And then I'm going to pair that with a Betty class in Betty homology, which there's a corresponding local system to this M of S, and I take a section of that local system twisted by paths in the base. I mean, the formal construction is here. I have chains on the base and local system of the fibers tensored over Q of pi 1 of the base. In any case, I have some horizontal 1 chains here, vertical n chains here, and sort of vertical 0 chains here, which are just choices of branches of t to the s. And then you put them together to get a period like this. That's a period of the Mellin transformed connection. And that's an entire function of S. This is the pairing of cohomology and homology in the original variation of Hodge structure. So this is already a motivic gamma, a motivic meaning that this was motivic. You can construct the gamma function in this way, but you have to start with an irregular connection. I mean, it's a very simple irregular connection. It's d minus t. So by just, standard tricks, you can show that if I replace M by dm, that multiplies this motivic gamma by S. if I replace m by tm, that substitutes s plus 1. And so if I replace mu by L mu and observe that L mu is 0, and then expand that in this way using the formula for Picard-Fuchs operator, I get 0 equals this, which gives me a recursion on the motivic gamma. That recursion on the gamma is actually the same as the recursion that results on the power series coefficients of the 0th period by just the standard method with the Picard-Fuchs operator. So that says that this motivic gamma at negative integers and A sub m satisfy the same recurrence with an assumption that will be proved, well, it comes out of the theorem in a second. So Black and Vlasenko make the decision to study the following particular gamma, which I call the conifold gamma. And that just uses cycles on U cross. It only uses in the horizontal direction the gamma naught that goes around 0 and the gamma c that goes around c. Okay, I mean, it's a complicated formula, and you have to write out a bunch, you have to write out the check that this is actually closed and actually gives a Betty homology class. But I'll skip that and just state their main theorem in a form that, their theorem, the way it's stated, it has a dualization, which makes it hard to use. And my contribution was basically to get rid of that bit and to specify this rational factor and so forth. Anyway, you get that kappa of S is actually equal to conifold gamma. So we call it the kappa equals gamma theorem, up to some factors, which are kind of trivial. This is some rational number. The first corollary of this is that the conifold gamma is 0 at positive integers, and at negative integers is basically just given by A sub m, the coefficient, the power series coefficients of the holomorphic period. And so kappa has this behavior at negative integers. So that's, again, the conifold gamma. Corollary 2 is that after a Q change of basis compatible with the weight filtration, the 0th column of omega lim, it can be written in terms of the derivatives of the conifold gamma at the origin. And because the conifold gamma is like this period of this total space, you can deduce from this that the limit mixed Hodge structure is the mixed Hodge structure of an actual motive. So this was known, say, for one motives, but no motive had been constructed that does this. There were conjectural motives that conjecturally did this, right? Constructed by Ayub and other people. But there is not, in general, a motive for a limit mixed Hodge structure. And so this gives a construction that works for hypergeometric limit mixed Hodge structures. So you define a divisor inside GM to the n plus 1 by this equation, and then you consider the fibration over the last GM factor that has fibers given by the original family cross GM to the n relative to the original family cross this divisor, which looks like this. Those are the fibers. And in the hypergeometric case, this IH1 inside the cohomology of this motive, this is some motivic sub, yields a submotive of rank n plus 1 with mixed Hodge structure periods exactly given by this. And so that gives a motive for the limit mixed Hodge structure at the origin. Finally, I just want to mention that both the higher derivatives of gamma beyond n and the values kappa of L at positive integers, which I call a priori constants, have Hodge theoretic meaning. And actually, the a priori constants have meaning in terms of a priori constants of Fano varieties when the X is a Landau-Ginzburg model, and are related to a priori's irrationality proofs for zeta of 2 and zeta of 3 in a couple of cases, and also to normal functions on higher Chow cycles. the idea is the a priori constants are in the d equals 2 case always special values of higher normal functions. And so if you want to read some account of this motivic gamma stuff, these are the 3 references so far, I guess. And thank you very much.